The M1 Abrams entered service in 1980 as a fast, heavily armored tank equipped with cutting-edge technologies to dominate the battlefield. Its combat debut came during Operation Desert Storm, where its plain, arid camouflage blended into the barren deserts of Saudi Arabia and Kuwait. Powered by a high-speed turbine engine, the M1 raced across challenging terrain to liberate Kuwait from Iraqi occupation. In 2025, the U.S. is expected to deliver a battalion of 31 M1 Abrams tanks to Ukraine to confront Soviet-era tanks once again. The Ukrainian army will require training to operate and maintain these complex machines, which, despite being over 40 years old, remain formidable due to continuous modernization and innovative design. Unlike traditional tank engines, the M1 uses a turbine engine, typically found in jet aircraft designed for high-speed operation with minimal waste. This counterintuitive choice for a heavy battle tank provides two key advantages. First, the Honeywell AGT1500 turbine engine is remarkably light, weighing just 1.1 tons while delivering 1,500 brake horsepower. In contrast, the V12 diesel engine of the Challenger 2 produces 1,200 brake horsepower but weighs 2 tons. This compactness and high power-to-weight ratio allow the M1 to carry extensive armor without sacrificing acceleration or speed. A comparison of torque versus shaft speed shows the M1's turbine engine has a significant torque advantage at lower speeds compared to the Challenger 2's V12 MTU 883. In its lightest configuration, the M1 weighs 61.8 tons, equivalent to 56 Toyota Corollas, which weigh 1.1 tons each, yet it can accelerate from 0 to 32 kilometers per hour in 7 seconds and reach a top speed of 72 kilometers per hour. The M1 primarily uses diesel fuel, which doubles as an additional layer of armor. Liquids excel at absorbing energy from explosions and kinetic weapons, particularly shaped charges. While it may seem risky to use fuel as protection, diesel is not highly flammable. A lit match dropped into diesel will extinguish rather than ignite. Diesel engines require immense pressure and a sustained flame to combust, making diesel relatively safe for this purpose. The turbine engine's versatility allows it to run on various fuels, including marine diesel, gasoline, or kerosene, simplifying military logistics during joint NATO operations. Post-World War II, Soviet tanks favored diesel engines, while Western allies used both gasoline and diesel, complicating fuel transport. The M1's ability to operate on multiple fuel types eases procurement in war zones and enables reliable performance in extreme temperatures, such as Ukraine's fluctuating climate, where diesel may crystallize at low temperatures, but kerosene can be used instead. The M1's turbine engine operates similarly to aircraft engines, but with key differences. Air enters the engine, where it is compressed by low and high-pressure compressors, each driven by separate turbine stages. The combustor, mounted perpendicularly to the engine, is accessible for maintenance with a simple bolted cover. The engine has two drive shafts. A secondary shaft, driven by the high-pressure turbine, powers accessories like compressors, electronics, and hydraulics, while the main drive shaft, driven by a dedicated power turbine, connects to the tank's drive sprockets. A recuperator, a large heat exchanger, surrounds the main drive shaft and its reduction gearbox, distinguishing this engine from typical jet engines. By preheating air from the compressor with exhaust heat before it enters the combustion chamber, the recuperator reduces the exhaust's heat signature, lowering the tank's visibility to heat-guided missiles and thermal vision while improving fuel efficiency. However, the turbine engine is fuel-intensive, consuming 4.2 liters per kilometer at a cruising speed of 40 kilometers per hour, compared to the Leopard 2's 2.2 liters per kilometer. The U.S. military deemed this trade-off worthwhile for the engine's ability to support heavy armor while maintaining high acceleration. The M1's armor has evolved over 4 decades, with specifics like thickness, materials, and layering classified. Early M1 variants used carbon composite ceramic armor, known for its ballistic resistance due to an extremely hard lightweight ceramic layer. In material science, hardness measures a material's resistance to localized deformation, like scratches. For example, industrial diamonds coat cutting tools due to their extreme hardness. The Vickers hardness test, which presses a pyramid-shaped diamond into a material, shows rolled homogeneous armor steel from World War II at 380, high-carbon steel at 550, and ceramics like silicon carbide up to 2,500, while being ceramics, though brittle, work effectively in composite armor with a tough metal backing. When a round strikes, the ceramic's hardness fractures the projectile, spreading impact energy across a larger area, which the metal plate absorbs. Compressing the ceramic with a faceplate enhances its performance against long-rod kinetic energy projectiles, dart-like, high-density tungsten rounds designed to penetrate armor. These projectiles create an abrasive maze of hard, sharp ceramic particles upon impact, gradually eroding the penetrator. Beyond ceramics, the M1 features a dense inner spall liner to counter spalling, where kinetic energy transfers through armor, causing internal material to splinter into deadly shrapnel. High-explosive squash-head munitions made from soft plastic explosives spread over armor to maximize energy transfer, fracturing the backing. Spall liners, initially lead and later depleted uranium in M1A2S and M1A2S, minimize this effect. Modern composite armor with air gaps can defeat squash-head munitions entirely. Reactive armor tiles, effective against shape charges, consist of an explosive charge between two metal plates. When a shape charge's hypersonic metal jet strikes, the explosive detonates, propelling the outer plate outward to disrupt the jet while the shockwave breaks it apart, with the tank's lower armor handling the resulting pressure. To avoid hits, the M1 can generate smoke screens using two systems. The first sprays fuel into the engine exhaust to create an opaque cloud, effective with diesel but risky with gasoline or kerosene which could ignite. The second system uses grenade launchers, either the 8-canister M257 or the 6-canister M250 controlled from the tank commander's seat, launching grenades 30 meters to form a shrouding smoke curtain. The M1 relies on a human loader rather than an autoloader, unlike many modern tanks. The U.S. views autoloaders as complex and less reliable, valuing the loader's role in maintenance, observation, and emergency support. The loader, positioned left of the main gun, accesses ammunition through a hydraulically actuated armored door, loading rounds as directed by the tank commander. The gunner, to the right, uses day and thermal night vision sights and a laser rangefinder to aim, while blowout panels on the ammunition compartment direct explosion pressure upward, protecting the crew. Early M1S used a 105mm cannon for compatibility with the M60 tank, but NATO's standardization push led to the adoption of the German Rheinmetall RH120. 120mm smoothbore cannon in the M1A1 and M1A2. This 5.3-meter, 3.3-ton cannon features a bore evacuator to clear propellant gases, preventing them from entering the crew compartment. The M1 uses two primary rounds, the M829 depleted uranium kinetic energy round and the M830A, one shaped. The tank's 52 to 68-ton weight necessitates a robust suspension. Unlike helical springs, which limit travel and bottom out under heavy loads, the M1 uses torsion bars inside the hull, raising its height by 150 millimeters but providing 38 centimeters of wheel travel, nearly double the M60's 20 centimeters. This allows the M1 to handle rough terrain effectively. However, the torsion bar system offsets road wheels, increasing wear on the leading wheel. Modern tanks are shifting to compact, adjustable hydro-gas suspensions, which the M1 considered but did not adopt due to their novelty at the time. The M1 has seen incremental upgrades across its M1, M1A1, and M1A2 variants, with enhancements like the M1A2S sights, auxiliary power unit, and remote-controlled Cross 2 system. Now, on the M1A2 PV for the U.S. Army is evaluating the tank's future, potentially with an M1A2 SEPV5 or a new platform. Despite its age, the M1 remains a vital asset, particularly for Ukraine in 2025, showcasing the enduring brilliance of its engineering. 2.1s.